This video demonstrates the use of tapir for motion planning for an autonomous ground vehicle. The environment is unknown at the beginning. As the robot explores the environment, it aggregates laser scan data into an obstacle map, as shown in the upper left corner. The Octomap library was used for this task. The tapir solver runs online during this simulation, as shown in the bottom left corner. At the beginning of the simulation, the human starts in any of these zones marked by circles. The robot knows the locations of these zones, but does not know the exact starting location of the human. The belief particles on the possible human locations are shown as green dots. There is uncertainty not only in the human starting location, but also in its movement velocity. If the human passes in front of the robot's laser scanner, the robot receives two observations, both of which are either true or false. The first observation is whether or not the human is visible. The second is whether or not the human is in a zone. Here the robot appears to be taking a longer turn than necessary. However, this actually allows it to have a wider view of the two zones on the left later. The goal of the robot is to watch over the human whenever he is in a zone. The robot receives a reward each turn, provided the human is visible and if the human is in a zone. It should be noted that the robot's action space is discretized into a total of 10 different actions. These consist of varying degrees of rotations and/or move distances. It would be difficult for the robot to follow the human through the narrow passageway. Therefore, the robot decides that the best course of action is to take a shortcut by navigating around the obstacles. In this problem, the robot is represented by the cylinder. The robot's goal is to tag the human by getting into the same grid square. The robot's belief is visualized by the coloring of the grid cells. A brighter green indicates a higher probability of the human being in that cell. The user is able to interactively add or remove obstacles during the simulation. The AVT solver is able to adapt to these changes and update its solution online.